When you press play with VR Preview, you appear in the center of this level. You have VR hands you can move and do different kinds of stuff. Here we have this level, and you can see in the middle there is an object called Player Start, located right here. When the game starts, game mode that we specified over here will spawn the default player pawn right in the position where the player starts is. In our case, it's called just VRPawn. Let's open it. If you'll open the viewport, you can see different components here. Among those, we have camera. That is locked to HMD. This means that the camera will be automatically positioned where the player headset is. Next, we have components that represent our controllers. This one for the left, and this one, for example, for the right. And here you can see we have our skeletal mesh representing our hand that is attached to our left controller. Let's open it. As you can see, our hand is represented as a skeletal mesh with different bones that we can manipulate later from code, from animation blueprints, to represent different finger movements. Now let's go back to logic, to our VRPawn event graph. We have a lot of stuff here, but don't worry, I will explain all of that to you. On begin play, first we specify what to consider as our tracking origin, then we set the pixel density, and then comes the input setup. This file here represents our input config. You can see for each input action we have different keys that will activate it. When those input actions get triggered, we can track that using events like we do over here. For example, this input action represents the left joystick move to the left or to the right. And here, as you can see, on started, we perform our turn based on the direction. Let's take a look inside this function. First, based on our Boolean input, we select the appropriate angle, whether it's gonna be negative or positive, and will give us the result going to the left by default or to the right. Here we're gonna set it to the local variable. Next, as you can see, we take our camera that, as you remember, is located exactly where our head is, and we save its world location and its relative transform. We're gonna use those variables later. Then we get our current pound rotation and add the angle difference to it. This is exactly the angle difference we have calculated before. Next, we get the pound location and calculate what transform the pound gonna have after the rotation. Here we add the desired rotation to our pawn. Next, by combining the rotated pound transform and the camera relative transform, and by getting the difference between the old camera location, we get how camera was shifted, and we add this difference to the pound location. This gives us the impression that we have rotated around the camera, not around the pawn. Next, we have our teleport that works with the right joystick. Here we have our input action, and the first one here is triggered event. It occurs continuously while we are moving the joystick. We are using this continuous event to update the trace and the visuals. If you remember, the trace looks like an arc, and we're using the projectile path prediction to calculate this kind of path. It returns to us the set of positions along this ballistic trail, which we're later gonna pass to the Niagara VFX system. The final hit position of that trace we're gonna set as our target teleport location. Here we handle our visuals visibility, based on whether our final destination that we have projected is valid for the teleportation or not. And then we toggle the visibility of the object that visually represents the final destination of the teleport. And next we pass all those points along the way to the Niagara system to represent this curvy line. This piece of code is detached and you can use it for debugging purposes. The next event here is started. It happens when we just move the joystick to the side. Here, first, we're gonna turn on the visibility of the Niagara trace system and spawn the object to represent our final destination. For this purpose, we're gonna spawn a specific actor. Let's take a look at it. If you will open the viewport, you will exactly see our final destination visualization. And the last event completed happens when we release the joystick and we have to perform the teleport. The first function here serves us as a cleanup. We turn everything off, destroy the final destination actor, set the visibility of the Niagara trace to false. And next, finally, we perform the teleport. And here, in case we have a valid final destination, we perform the teleport using our camera offset. Next, what I'm gonna show you in this lecture is how we manipulate the fingers. So all these events are specifically used to pass some variables to the animation blueprint that will then manipulate the bones and represent the finger movement. So I'm talking about this. It happens when you touch and release the buttons on your controllers. So all those values go to the animation blueprint on our skeletal mesh hands. This is our animation blueprint. Let's first take a look at the event graph. First, we check whether we have to mirror the hand. This is used to represent two different hands, left or right. One is just mirrored. And here we have some basic interpolation code, so we do not use the input values directly. We use an interpolation to make it more smoothly. And this is exactly our animation graph, where, based on those input values, we just perform blending between different animations. Every animation here affects the rotation of specific fingers. By blending between them based on the input values, we can separately manipulate different fingers. For example, this animation, if we're gonna take a closer look, manipulates only the point finger. And this one is the thumb. So all those values are passed directly to the animation blueprint over here. You can see right here we're getting the left hand, getting its animation instance, and directly setting the variables that then appear over here. I think it's enough for this lecture, and we will continue in the next one.